Hello.
Morning. Can you hear me? Hello?
Hello, Anders. Yes, I can hear you.
Great. So Lucas and Willem are online. That's fine.
Here in Ghent it's rainy. So might be that some people decide to stay at home. So all these lectures will be recorded and I will put them finally on YouTube, but only on a private channel, so that people who have the link can see it and others will not see it. It's still 1 minute to go. So slowly start. I'll write the title on the board. Start with a new section. Phase transitions for the Hydra battle. Now, whatever this is, I will explain in a minute. Still waiting for some more students, but well, my mobile phone says it's 10 o'clock. So. Anyway, so to start, first of all, today's lecture will be the lecture of today will be very simple, elementary, but it has also should have some entertaining factor. First of all, assume that you are at the party and there's a certain game played. The game is who can name the biggest number? Okay, now when you're clever, you wait for the answers of the others and then normally you win, right? You just add 1 to the the one to the maximum of the others. But just imagine you have to write down a number on a sheet of paper, not seen by the others, and then you want to win. And one possible way to win is you write this snake on the board with 9 heads and tell, yeah, the number I want to describe is the number of steps Hercules needs to win against this Hydra. And normally you would win. Even if people would know the Ackermann function, it will not help them. So that's a good guess. Now we want to study why this is so interesting. First of all, we want to study what is behind this Hydra. Let's say, what is the description of it? And then we want to study how big these resulting numbers become. And finally, we want to study the underlying phase transition, which makes these battles long or not so long. Well, you have not missed anything. I just gave some sort of easy introduction. Now, first of all, where does the Hydra come from? The Hydra comes from Greek mythology. And so it starts with the gods, Greek mythology. So here we have one famous guy, godfather of the gods in Greek mythology. This is Zeus. Okay, and Zeus had a wife called Hera. Maybe over here. And Zeus had a son. Right. The son is Hercules. So here comes Hercules. Awful guy. Now, what's the story? Well, what you would expect is following Hera. And here is Hercules. Now, the story starts with the following, namely, you see here the nose smile. So there was something wrong in the story. In the story, what is wrong is Hercules was the son of Zeus, not of Hera. And here is some other nice girl. It's Alcmene. And so they had together a son. Now you can imagine Hera was not happy with this, right? And so what Hera did is she thought about a punishment. So she punished now Hercules for the situation, not her husband. So what she did is she made a certain Eurystheus be the boss of Hercules, and Eurystheus could claim whatever he wants, and Hercules had just to fulfill the wishes of Eurystheus. And Eurystheus somehow invented certain very difficult tasks, which are basically impossible. 10 tasks, something like 10. And one was to kill the Hydra. Now the Hydra was a dangerous snake, 9 heads, and he was sort of terrorizing the environment. And so Hercules was supposed to kill the Hydra. But the problem with the Hydra is, okay, you go to her and you have a sword and you cut off the heads. And after 9 steps, you're done. But that's not the case. The Hydra is a beast, namely when you cut off one head, every now and then you get many more heads. And so there's no clear strategy to win against the Hydra. Now what we do here is we make the story into mathematics. Or logic. And we proved two things, namely that Hercules always wins. And that is complicated in the sense that it's so complex that pure arithmetic is not able to prove that Hercules can win. Now we do not do proof theory, but we connect this Hydra game to functions which are very quickly growing, even quicker than the Ackermann function. Now we have to say, what is now Hydra? And when we abstract the underlying structure here, we have here a body, which is a root. And for the rest, it looks like a finite tree. And that's our definition. So 3.1. Definition. So what is the Hydra? The Hydra is a finite rooted planar tree. So planar tree just means when I draw the tree on the board, there's a direction between the immediate subtrees from the left to the right, and this ordering is somehow to be respected. So I can speak about which tree is to the right and which head is to the right and which is to the left. Anyway, that's all. And now we model the story how Hercules was winning against the Hydra. Now, of course, when the Hydra is always getting new heads, Hercules can never win. So there was yet a helper, Menelaus, and he was coming with some fire, and every time when there was a head cut off, he was able to burn this position so that there could be no new subhydra showing up. So we want to model this in some way. So we assume that Eularus is not the biggest person on the Earth, so that he can only reach to height 1. So when there's height 1, he can somehow help Hercules. Okay, now model the Hydra battle. So we have discrete time steps, 0, 1, 2, 0. We have discrete time. And at every time step, Hercules can perform an action, namely chopping off one head. Not two at the same time, just one head. That's all fine. So how does this go? Assume that we reach time and the Hydra transforms into, after I made a step, this form HI. Now there are certain cases. Now we wanted to show, so at time I, Hercules chops off one head, and then the Hydra transforms into Hydra HI plus 1. So if HI has a form so we do a graphical representation. So we have a tree where there's one rightmost head of height 1. So it's just the body of the Hydra, there's one head showing up. Then if this is HI, then HI plus 1. That's, yeah, well, okay, step is. So Hercules is not thinking very much. He's just following a sort of trivial strategy. He chops off this head. So the Hydra is this one, and the head is disconnected. So it's a dead head. Now, this means if the tree itself has only height 1, Hercules wins after 500 many steps. That's fine. But now, if HI has a form, now we assume that the rightmost head is at a higher position. So now we have to model this somehow. So we have here sort of situation. This situation. And it is important that this position here is not position over here. So it's somewhere higher in the tree. There is a subtree of this form. Oh, that's right. Yeah, again. We have X coming over here. And here's some subtree. As this form. So there is a head of height 2, at least 2, but can be higher. Then we go down. Here is a remaining subtree to the left. And here's a context where we went to the rightmost head. Okay. And what? Copy the context. And cut off this head. Okay. Now the question is, what do we do with this part here? Now, if you would just do it like this, then there would be a head disappearing. What is going on is this part is multiplied by many times. And of course, if you are at step 100, you have suddenly 100 new yeah.
Are those lifetimes connected to the rest, or is there a gap?
Well, they are connected. So this here is dots, so to say. So this context is basically going up to this position. Well, somehow would have written it like this. It has to be connected to the rest.
Okay. Yeah.
So and hello. And the point is that I have here. Well, let's see whether I did it right. Not fully. But there's this form. There should be at least height 2. And there's this form. Yeah.
So does it also mean that the vertex that is connected to the head? Oh yes, has only degree 2. Not 3. I mean, it's only going.
Maybe I write it this way. Fine. So it's the outer degree of this head. This node can be larger than 2. So say there's one rightmost head, then there's some subtree left over here. But it's important that there are at least two points. And what I'm doing is I'm cutting off this one, and I get this structure over here. Into this structure. But this structure is copied. So here's a branching of I, and I have a reduplication of I many subhandlers. So that's a sort of a tricky business, but that's the Heider battle. And now let's say that Hercules wins against H if there is the number m such that for Hydra H0 at time 0, the Hydra is H. Then we have H, we take H0, and we take this result, divide it time 1, and we divide it time 2. At some number m, we hit just the root. And then you can implement this Hydra battle on your laptop. And what's going to happen is you implement it, this Hydra, and then you will get a stack. And so that's a sort of surprising. And the theorem is the following. Namely, first of all, A, Hercules. Always. Against any Hydra, Hercules wins. That's already some information. Actually, here we are discussing chopping of almost the rightmost position. Actually, Hercules can do whatever you want. He can also chop off in the middle. So Hercules wins always, but we just formalize it in a deterministic way. And B, not able. That's surprising. Now we are not doing proof theory here. So what I will do is I will give a result on the growth rate of how long the battle lasts. And this takes an enormous amount of time, which will be measured by a fast-growing function. And we will do this one. And the course on proof theory will learn that the totality of that fast-growing function is not provable so in pairs. So this, there's a problem. The problem is when you do usual mathematics, you will have a hard time in showing that Hercules wins. So when you just do discrete mathematics, you will have problems because normal discrete mathematics can be carried out in arithmetic, and we just have seen you don't expect to win within arithmetic. So we now introduce a tool. And the tool is transfinite object. And the point is sometimes you can use transfinite objects to prove results about finite objects. And that is what we are doing here. There's a magic with infinity. You look somewhere to the stars, and then you see it has consequences to the real world. So we are considering a well-founded structure, but I will just write down the structure and then I will prove the well-foundedness. So let E be a subset function. Let numbers and numbers be defined by the following two clauses. First one is the constant zero function in E. Is zero of zero. And second, if alpha and beta in E, then a certain function of omega to the alpha plus beta is in E. With a definition omega to the alpha plus beta, x is x to the alpha x plus beta x. And I say alpha is less than beta, perfect only if they exist with k. That's it for all L, equals k, and we have alpha L is smaller than beta. This basically is some sort of order of infinity, already studied by Hardy in 1900 and something, 1904 maybe. And what we are going to prove now is interesting theorem 3.4, namely that E with the Piaget relation is a well ordered. Now there are two ways to prove this. One is using ordinals.
Sorry, can you hear me?
Yes.
So condition 2, I couldn't read the first. So if alpha and beta are in our
E.
class, then
Then new function omega to the alpha plus beta is in E. Where omega to the alpha plus beta of x is a function defined as x to the alpha of x plus beta of x.
okay, omega x is the function. Okay, yeah, sorry. Okay. I
problem.
wasn't. Yeah, no problem. I was a bit confused with the symbol of omega, but now no problem.
There's some reason for the choice, and this is omega, but it will become clear in a minute. So that's an interesting result, and we prove this just by bare hands. So prove this one. Well, there are two aspects. We have to show that this is a linear ordering and that this is well-founded, that we don't have an infinite descending chain. So, how can we do so? Well, we can order these functions in the following way. So, to prove it is linear. And we do this by induction on the term length of the functions involved. We say the complexity of alpha and the complexity of beta is smaller than the complexity of omega to the alpha plus beta. So, of course, they're shorter descriptions. So, for this, assume, well, of course, assume that alpha is not zero, because zero is smaller than every other element. So assume that alpha is such a form, and then beta is also such a form. And if I develop beta further, so I can assume that alpha is a form, a sum of m1 many omega to the alpha ones plus beta 1. And beta is a form omega to the alpha 2 m2 plus beta 2. So with these m1s, I take finite forms, finite sums of equal elements. Now by induction hypothesis, I can compare those terms with those terms. So assume that omega to the alpha 1 is bigger than beta 1. and omega to the alpha 2 bigger than 0. Okay, now what? I make our cases thinking. By induction hypothesis, I can compare the exponents here, so these exponents, and I can consider the case alpha 1 is smaller than alpha 2, or alpha 1 is equal to alpha 2, or alpha 1. So if alpha 1 is smaller than alpha 2, then what is going to happen? Well, so beta of x is x to the alpha 2 of x times m2 plus beta 2 of x. Now,
It should be omega of the
yeah, well, I already replaced the omega by x.
Oh,
Let's say I plugged in here already the definition. Now this is bigger than what? So beta 2 is smaller than omega alpha 2. Then we'll see in a minute that beta 2 is less than or equal to omega to the alpha 2 minus 1. So this will be bigger than x to the alpha 2 of x minus 1 times x for x large enough. So this term here will be at least as big as this one. And this one here is x to the alpha 2 of x, which is the same as this term. Yeah, but this one is bigger than this term because this term is just one of those. Right? Okay. And this is bigger than alpha of x, because alpha 1 of x is always, well, for x large enough. So alpha 2 of x is dominating alpha 1 of x, because we have assumed that alpha 1 is smaller than alpha 2. So alpha 2 of x minus 1 is at least as big as alpha 1. And now we have here x becomes unbounded, x becomes bigger than m1. And if you make x even bigger, we also dominate the beta ones. So we see this one. How is the case? Alpha 1 is equal to alpha 2. And m2 is bigger than m1. Then you can argue in the same way. We got alpha 2 times m2 plus beta 2 of x will be x to the alpha 2 of x times m2 plus beta 2 of x. Now this one, same as for 1 of x. Now m1 is smaller than m2. So f here times m1 And of course, M2 is bigger than M1. So M2 is at least as big as M1 plus 1. So this is the least as big as this one plus x to the x to the alpha 2 of x is bigger than alpha 2 is alpha 1. Omega to the alpha 1 is bigger than beta 1. So eventually, this one is bigger than beta 1 of x. So we get here x to the alpha 1 of x times m1 plus beta 1. And finally, here's the case alpha 2 is smaller than alpha 1. But then it cannot be, if alpha 2 is smaller than alpha 1, we can change the roles here. Then beta will be smaller than alpha. So if you have yeah. So what is the remaining? Is the case alpha 1 is alpha 2. M2 is smaller than M1, and you can change the rules, the roles, and then alpha would be smaller than beta. So finally, what remains is if alpha 1 is alpha 2, and M2 is equal to M1, and you can compare beta 2 with beta 1. Yeah.
We are using injection, right? But
Yes.
well, why can we use injection? Because it's we haven't proven yet that it's well founded.
We are using induction on the length of a description. So the complexity of alpha and the complexity of beta is smaller than the complexity of omega to the alpha plus beta. And we are using induction on the complexity, but not on the ordering, so to say.
Okay.
So this is a lot of tricky business. Usually, formally, we can use an approach using universal algebra, and we have to introduce terms for annotations. And we do induction on terms, which yeah.
Why do we have to introduce M1 and M2 again?
There's no need actually to do so, but it makes this case somewhat easier. So with M1, I collect the same occurrence of the same term. So that I have here the situation, I can write the number this way where beta 1 is smaller than omega to the alpha 1. But this is a matter of taste. So now we were here, and this is somewhat easy, because then alpha of x is the alpha 1 of x times m1 plus beta 1 of x. So beta 1 is eventually smaller than beta 2. So alpha 1 is the same as alpha 2, m1 is the same as m2, and beta 1 is eventually dominated by beta 2. So this term is eventually dominated by this one, which is beta of x. So what's going to happen is the following. So we have two terms, alpha and beta, and then we consider the possibilities. First, we consider the exponent, the leftmost exponent. compare those ones by induction hypothesis. And when one is smaller than the other, we get an argument for domination. Or it happens that these are the same. Then we compare the coefficients over here. And if those are the same, then we compare the rest. So actually, we have a lexicographic ordering with 3 tuples, with triples. That's basically it. Now, I did a bit of so implicitly I used a lemma. So we needed some sublemma, namely if the function beta is bounded by omega to the alpha, then beta x is bounded by x to the alpha x minus 1 times x for x large enough. So remember in the beginning I made this transition to these numbers, and here I made an estimate with the exponents, and basically I used this property. Now this is interesting, but it's easy to prove. So because the following, it works because if beta from omega to the alpha 1 times m1 plus beta 1 with beta 1 smaller than omega to the alpha 1, then beta of x is smaller than omega to the alpha x to the alpha 1 of x times m1 plus beta 1 of x. Now this one here is bounded by x to the alpha of x minus 1, large enough x. So alpha 1, but if this one is smaller than this one, it cannot be the case that alpha 1 is equal to alpha, and cannot be the case that alpha 1 is bigger than alpha. So this one has to be smaller than this one. This one is smaller than alpha, therefore alpha 1 of x is less than or equal to alpha of x minus 1 times m1. But now I can make here x smaller by letting x be bigger than m1. And beta 1 is smaller than omega to the alpha 1. Omega to the alpha 1 is smaller than this function. Maybe I write it in this way. So if x is large enough, x minus 1 is finally bigger than m1. Here I have beta 1 is bounded by this function, so it's bounded by x to the alpha x minus 1. This is less than or equal to x to the alpha x minus 1 times x, and this is basically x to the alpha. So this is interesting. And what it also shows, this argument shows if beta and gamma are smaller than omega to the alpha, then beta plus the function beta plus gamma also smaller than omega to the alpha. Because both functions are bounded by this function, and when I make x big enough, the exponential function also is stable under additional functions coming from beta. Okay, now comes the part of this is sort of combinatorics, which is usually not carried out, but it's also some usually left as an exercise. Now the difficult part is the well-formed. So this argument which I gave until now is elementary combinatorics. And okay, so now we want to prove that E with Lysen relation is well important. Now, first of all, we have to show for alpha and E, there exists an L such that alpha is bounded by omega index L, where omega L is defined as follows. Omega 1 is omega, and omega index L plus 1 is bounded by the same as omega to the omega L. So it's an iterated exponential. Why is this the case? Well, basically, you look at the arguments. If alpha and beta are in E, then by induction hypothesis, you have iterated exponentials for alpha and beta. And then you have here a new exponential. You make your tower over here one bigger. And then you see that's going to work. So, well, proof. Assume that alpha is a form omega to the alpha 1 times m1 plus beta 1. Induction hypothesis. So we do this again by induction on subterms. Alpha 1 is bounded by omega n. Now, this is basically the same argument as usual. Then alpha 1 basically we can use that one over here. The other one is bounded by this one. Or we use this one over here, right? Then omega to the alpha 1 is bounded by omega to the omega to the L. Now we take n many terms. One by this number. And beta 1 is smaller than omega to the alpha 1. So by iterating this argument, using this one again, you get here. Why are we doing this? Because we prove the well-foundedness of E by doing it in states.
Excuse me, Professor. Could you maybe repeat what the last statement was? Because I can't really read it.
This one?
No, your last step. Yeah.
Last step. So we are applying this lemma. Beta gamma is smaller than omega to the alpha, implies the sum is smaller than omega to the alpha. So by induction hypothesis, omega alpha 1 is smaller than some omega index L. Then we raise it to power, and omega to the alpha 1 is eventually dominated by omega to the omega L. Now we apply this one, namely omega to the alpha 1 plus omega to the alpha 1 is smaller than this number. So by iteration, omega to the alpha 1 times m1 is smaller than this number. We have already this one, and now we have to look for the remaining beta 1. Beta 1 is bounded by omega to the alpha 1 by writing alpha in this way. And then beta 1 is also smaller than, beta 1 is smaller than this one, therefore smaller than this one. And we can again use this one now for beta equal to this number and gamma being beta 1. So again, we use closure under addition. Omega to the alpha 1 times m1 plus beta 1 is smaller than omega to the omega to the L, which is omega index L plus 1. Is this clear? Or
Yeah,
not?
thank you.
Okay. So now we show what? So that the set of alpha smaller than omega L is well formed. And we prove this by induction on L. Assume that we have this. If true, then the whole set is well formed. Why? Well, if we have the sequence alpha 0 bigger than alpha L, strictly descending, then we know then there is some L and N such that omega index L is bigger than alpha 0. And then this one would not be well founded. So if we have shown that all these sets are well founded, then the whole set is well founded. And this is now the trick where somehow we use complexity. So it becomes more and more complex. The higher the L becomes, the more complex it becomes to prove the well-foundedness. And we do this by induction on natural numbers. So first of all, when we have L equal to 1, so when alpha is smaller than omega, this means alpha is a function smaller than the function x goes to x. And then we see that alpha has the form of the constant k. So this means if L is 1, then this is an isomorphic copy of the natural numbers, and they are well formed. That's fine. Alpha smaller than omega 1 is order isomorphic to the natural numbers. Now assume therefore that instead of alpha smaller than omega L is well founded. And for contradiction, assume that this is not well founded. Yeah, then what I do is I pick an infinite descending chain. Oh, let alpha I be an infinite descending chain in the sets. Now we write every alpha I in well, every element in E is some sort of sum of exponentials. So we can write alpha I in the form omega to the alpha I1 plus omega to the alpha I in I. And now I have linearity, so I can assume that the exponents are ordered, where alpha I1 at least as big as and at least as big as alpha I in I. Okay. What we are now doing is we construct an infinite tree, which is finally branching, and this will have an infinite path. And the infinite path will be built by using the exponents of alpha I. Now the exponents, so alpha I is below this number. Then all the alpha I are smaller than omega L. And so I have to somehow find the descending sequence of exponents. But the problem is, it's not so easy to just pick those sequences. They come by some abstract argument. Now construct the finitely branching infinite tree. And the tree will appear as a union of finite approximations. So it's time 0. The first approximation is the following. We take a tree, and then we plug the exponents of alpha 0. We have alpha 0, 1. Here is alpha 0 and 0. And for some reason, which is not really important, it's like here -1. -1 is just some sort of new minimal element of the ordinals. That's not really important. That's the first approximation. Okay, now, and it's also ordered from the left to the right. Minuses are just showing up on the right hand side. Okay, now assume that we constructed approximation at time I. Now what you see here, the leaves are ordinals or -1. So where the leaves are exponents of alpha I or -1. Now we compare alpha I plus 1. Omega is alpha I plus 0 plus omega alpha I plus 1 and I plus 1 smaller than alpha I, is omega alpha I0 plus omega alpha I. Okay, now we have to figure out how to compare this stuff. And what we learned here already is basically how to compare those two orders, alpha and beta. We first compare these exponents and then the rest. And when we spell this out, it comes down to two cases. One case is this is the strict subsequence of this. This means this to me has less terms over here, but the beginning is the same level. So if we have the situation, then what? Alpha I k, alpha I plus 1k, for all k less than equal to n I plus 1. This n I plus 1, and assume that this is smaller than n. Then we do what? Well, we have some picture. So we have here our tree. Here are the alphas. Alpha I 0. Here's maybe alpha I n I. Different minus ones. Whatsoever. And let's say this alpha I n I plus 1, which is the same as alpha I plus 1 in I plus 1, right? So here in the beginning they are the same, but n I plus 1 is smaller than this one. What we are doing is then we leave those leaves over here, but we take all the ones to the right, and we plug in here -1. So this means the overshooting elements are getting a new leaf -1. The effect is when you do so, in the new tree, the exponents are from alpha I plus 1, or they are -1. It's just this case. And now the other case is we have this type of lexicographic comparison. So at some moment, if alpha I plus 1 is smaller than alpha I, in the beginning they will be the same, and at some moment there will be a term here, which is bigger than the corresponding term here. So second basis is I k alpha I plus 1 k for all k is not some L, where alpha I at some moment there is a transition. There's the first element on this side, which is bigger than the corresponding element here. But now, if there's some exponent bigger than the corresponding exponent over here, since we assume that these elements are strictly or weakly decreasing, then this single point here is bigger than the whole sum. So this is basically the critical decision. Now, we assume what? At time time, we have what? we have here a tree. And in a certain moment, there is alpha I L plus 1. Here is alpha I L plus 1, alpha I 0. And here's some more stuff, and here are some minus 1. Now, what are we doing? Then in the transition, we have time I here. In the transition from I to I plus 1, we extend this node and plug in here alpha I plus 1, I plus 1, up to alpha I plus 1, and I plus 1. So all the rest in alpha I plus 1. So here we have this big as alpha I plus 1, I plus 2, up to alpha I plus 1, and I plus 1. So all the remaining exponents are plugged in over here. And for the rest, we plug again in minus 1s for the exponents in alpha I, which are no longer used. So the point is, if we assume that at time I, we have exponents from alpha I and minus 1, then in the new situation, we have exponents from alpha I plus 1 and minus 1s. Okay. Now, what we see is that the tree at time I is contained in the tree of time I plus 1, because I only added new nodes. There's only something coming on top. So this means what's going to happen, we can take the union. Now, what we also see is at every step in the construction, we added always a minus 1 node. So at time I, we have at least added, at every step we have added 1 node. At time I, we have at least I many nodes in the I approximation. If we take the union, it will be an infinite tree. As the branching of the tree, every moment we guarantee there are only finitely many immediate successors. So it's a finitely branching tree. So by Koenig's lemma, we get the path, get an infinite path to the tree. No. And then if you look at the ordinals that to branch, we'll see that the ordinals will be decreasing because I replace bigger ordinal always by a set of smaller ordinals. Okay, so what we obtain is we obtain an infinite plane, infinite descending of exponents in set of alpha smaller than omega f. That's a tricky proof. And this is a well-founded proof. Well-founded proof for this structure without using ordinals. So they just circumvented it. And this argument is somehow showing how strong this principle is. Now we are using the structure E and smaller to prove the determination of the hyperbettel. So we move the sequence of hydras. So what the goal is to find mapping or from the hydras into let's say E, such that the ordinal of hydride time I is always bigger than the ordinal of hydride at time I plus 1. And now we are going to do so. For this, I will introduce lots of notations, and what I will first do, I will do two things. I will prove this one. For this, I don't need much. But I also want to associate this hyperbettel to fast-growing hierarchies. And for this, I need extra structure theory for this one, which I will also develop. So, first of all, come from technical definition, which I use basically implicitly, which I already used implicitly. So I say alpha, it's a normal form, omega to the alpha 1 plus omega to the alpha n, if alpha is such a sum, and we have already the exponents in the expected way. And I say two elements in E are in normal form. So if alpha is a normal form, omega to the alpha 1 plus omega to the alpha n, and beta is a form omega to the beta 1 plus omega to the beta m, and alpha n is at least as big as beta 1, then we write normal form applies to alpha and beta. Now, what is the trick here? We cannot see it yet, but it has to do with the effect when we think about the underlying structure of ordinals, and we want to form the addition of alpha and beta, then in normal ordinal addition, if alpha n would be smaller than beta 1, then there would be some cancellation showing up. And by writing down sums where this normal form condition holds, then there's no problem with cancellations. Now I define also what does it mean to have a sum. Now I need to be careful because at the moment I use the sum as pointwise addition. Now I use the formal sum on ordinals. So if alpha form omega to the alpha 1 plus omega to the alpha n. Beta is the normal form omega to the beta 1 plus omega to the beta m. And if L is maximal with property. Alpha L is at least as big as beta 1. And if L does not exist, we take L equal to 0. Then alpha plus beta is defined as omega alpha 1 plus omega to the alpha L plus omega to the beta 1 plus omega to the beta n. Okay, and if alpha is the form omega to the alpha 1 plus omega to the alpha n, normal form. Beta is the form omega to the alpha n plus 1 plus omega to the alpha n plus m. Then alpha plus beta is omega to the alpha p1 plus omega to the alpha n plus m, where p is a permutation of the numbers such that alpha p1, so this is because alpha pn plus m. So when we form this sum, this is called the natural sum. It will also be the natural sum of ordinals. Then we rearrange the exponents in a way that no cancellation like this is shown. Now, one has to be careful, namely when one works with the functions in E. This plus is always the natural sum, because on the natural numbers there is no cancellation. So in fact, we have alpha plus beta of x is the same as alpha of x plus beta of x pointwise. But it's not going to happen with this definition. In general, alpha plus beta of x is only less than equal to alpha of beta. I will be careful in dealing with this, but don't worry too much. In practical applications, I will only use sums when the system coincides with this. So I will always assume certain normal form conditions. So there's no problem. Okay. That was E. Then comes E. I finish the definition and then I go into the reg. Now I will define, well, there's three types of elements in E. One is the constant 0, which I will identify with number 0. Then I have terms of the form alpha plus omega to the 0, which is the paper type. And I have elements in E which are limit elements. Limit elements have the form as some beta plus omega to something which is not 0. Now, of course, one has to be careful with forming the sums. So here I assume some Cantor-normal form, where this appears on the rightmost position. Okay, now the fundamental sequence is as follows. If alpha is equal to 0, then there's nothing to convert against. Alpha remains constant. if alpha is the successor, then I have no canonical convergence. I just jump to the predecessor. Now assume alpha is a limit. Alpha is a node form. And the alpha 1 is omega to the alpha n. Now there are two cases depending on whether alpha n is a limit or a successor. And if alpha n is a successor, then alpha x will be x is those ones, and then plus omega to the gamma times x plus 1. Now this is basically the intuition which we have, that the elements smaller than omega to the gamma plus 1 are eventually dominated by terms coming from below, and these are omega to the gamma times finitely many some finitely many terms of them, and if x becomes a variable, it is forming a convergence sequence. So terms of this type converge to omega to the gamma plus 1. And finally, if the normal form omega to the alpha 1 plus omega to the alpha n, and assume that alpha n is a limit, so not of this form, not of this form, then either by recursion on subterms or by recursion where it's assumed that alpha n is smaller than alpha, then alpha x is defined by recursion, it's omega to the alpha 1 plus omega to the alpha n, then I can take the parameter sequence alpha n. So lim is a set of alpha. Alpha is different from 0, and in not the case if there's this beta that plus 1. And yeah, we say if you take alpha and beta, we can step down from alpha along x to beta. This one only is. So we take alpha. Then we step down along x. Takes this result, step down along x. And we do this n many times. At some moment in beta. So this means alpha is bigger than beta, and by stepping down the fundamental sequence along x, some moment I will hit beta. Now, if alpha's limit is clear, I'm stepping down along the fundamental sequence, and therefore I have these technical other definitions when I hit somehow a successor and stepping down, I just go to the predecessor, and when alpha some moment hits 0, then it stays.
Sorry, is it possible to like the line where you written down the clause for alpha in its normal form where the exponent is a limit term? So what's then the step? It's like
Yeah, here.
just yeah.
We define alpha of x, and defining alpha of x, I assume that I know what alpha n of x is.
Mhm.
So I define the fundamental sequence for alpha, but alpha n is smaller than alpha, so by recursion I can assume that alpha of n at x is defined.
Mhm. Ah yeah, okay.
Then
It's just a
I
recursion.
take alpha of x is, I take the stuff from alpha, and in the exponent I plug in instead of alpha n the alpha n of x.
Okay, and then of course we have the previous clauses to determine again.
So
Okay.
maybe it's good to see some example. So we have the identity function. We have omega to the omega of x. It's omega, and then I fundamentally provide you. We have omega to the omega of x. This is omega, this is omega, this is plus 1. So you see basically this type of what you would expect, right? And of course, there's some sort of continuity involved. The idea is if alpha is some sort of beta plus gamma, this is somehow in some normal form. If he has this normal form condition from over there, then alpha of x is beta plus. And this respects so if so the fundamental sequence is in some sense continuous with respect to addition and exponentiation. So omega to the lambda it's omega. Okay, and to finish our discussion,
And can I also,
yes,
yes, you would say, in F, we define alpha when alpha is big, we define alpha bigger or equal to beta and not equal, then it's equivalent to that. But if you choose beta the same as alpha,
yeah, it comes next. Then I write this one. This is alpha equal to beta or alpha steps down. So the reflexive closure of this relation is written this way. But here's a strict descent involved, minimum one step downwards, so beta is smaller than alpha.
yes, but if you choose on the right hand side, the m as 1.
Okay. Let's say it is at least as b plus 1. Okay.
So, if you choose then 1, then you would just get alpha.
I get always an order smaller because only alpha has to be not 0, otherwise it doesn't make sense, let's say. Okay, maybe I should write an alpha less than 0 just to avoid a lot of nonsense cases. So this should be a strict ordering, but you are right. As it was written, if alpha would be 0, then alpha 0 would go to 0. Because 0 of x is 0. But I really want to have a strict stepping down. So alpha is non-zero. From alpha, I can step down to x. And there is a sequence, start with alpha, minimum one step, go down to alpha of x. It could be that I hit beta, but it could be that I didn't meet it, then I go down. Now it's not the case, this relation is not the same as alpha is smaller than beta. Because you can imagine you have omega, and if you step down, and it's correct. Omega steps down along 100 to 10. Just can apply the definition. But when you have here big number, let's say 1000, and this is 1. Because from omega, you step down along 100 to 101. From 101, you're not able to get down to 1000. So it means there's a certain restriction in the way where I can jump to. And the final notation which I want to show is just technical stuff, don't matter that much. The maximum coefficient of 0 will be 0. And if I write alpha as omega to the alpha 1 times m1 plus beta 1, where beta 1 is smaller than omega to the alpha 1. This is always sort of normal form. Then the maximal coefficient of alpha is the maximum taken over m1. The maximal coefficient of alpha 1, maximum coefficient of beta. Oh, this is unreadable, I guess. So in this case, the maximum coefficient of alpha is the maximum taken over m1 the maximum coefficient of alpha 1, the maximum coefficient of beta 1. Now, what is the point? The maximum coefficient is, in some sense, the biggest natural number which shows up in term representations of alpha. It will play a role in the next lemma, but now it's a moment for a break. So it's now 25, so 15 minutes break. What is going to happen next? I will explain the theory of fundamental sequences. I will define the Hardy functions, and I will show some basic results for the Hardy functions. And then, if enough time is left over, I will show termination of the Heider battle. And if I'm not able to show termination today, then I will show it next Friday. Now you can imagine what is the idea with the phase transition. So I have here Hydra HI is Hydra HI plus 1. And then we had this thing with how many multiplications, but you can replace I by f of I. And then we can ask what's going to happen when we replace the identity function by log function. Is it still complex or not? Or a double log function? And the answer is, if you take a finite iteration of logs, it still becomes complicated stuff. When you do log star, it becomes simple. And the Heider terminates within P. There's also a paper about what is going to happen when you chop off the leftmost set. That's the rightmost, or is the leftmost set? Good question, right? And then Hercules wins within PA. Approval PA. So it does make a difference whether you cut off from the right or from the left. But anyway, we are studying the complicated version. The most stupid way Hercules is doing is going to the rightmost set. And one can prove that this is the longest possible, takes them the most of the time. But anyway, so now it's time for, so I continue about 15 minutes. So we continue in about 7 minutes.
Okay. Excuseer, professor.
Ja.
Ik kreeg hier een vraagje binnen. Er was een vraag of dat u of het eventueel mogelijk is om notities in te scannen die op uw voorraad te plaatsen.
What? Dus kunnen we even herhalen?
Ja, er was een vraag of dat u uw notities eventueel zou kunnen inscannen of dat mogelijk is voor dat op uw voorraad te plaatsen.
Wat inscannen? Dus,
De notities of zo die u gebruikt.
goede vraag. Dus nu voor dit stuk voor die Hydra of?
Ik denk het, ik ga eens vragen.
Ja, dus het
ik
is
denk
zo,
wel.
zeg maar, dat voor de Ackermann-functie en Kahneman, McLuhan en Peres-Haring, dat was in de artikels al, ne?
Ja.
Ja, dit hier is eigenlijk ook in een artikel, maar niet helemaal. Dus de behandeling van de functieklas E is zeg maar een beetje niet standaard. Maar goed, ja, kan ik doen. Dus,
Ik heb het denk ik gevonden, wat het classifying phase transitions for thresholds, for Kutzing sequences en Hydra games.
ja, dat is...
Die heb ik inderdaad
ja,
openstaan.
dat is juist. Dat is het eerste artikel. Goed. Maar ik denk, we kunnen verder gaan. So, people are back.
Professor, de vraag, ik kreeg net de vraag was of het aan het algemeen kon, blijkbaar. Of voor stukken die niet in artikels staan.
Ja, dat kan. Dus wel, als ik het vergeet, laat maar weten. Dan, maar in principe kan dat wel, ja.
Oké, dank u wel.
Ja.
Ik zal het doorgeven.
Okay, so we continue. So last lecture we looked at the Hydra battle. Just remember what was the rules of the game when HI it's a simple form like this. It was clear that HI plus 1 was just this one. Now, when HI at a specific form, like this, and just to repeat, the point is, maybe it was not completely clear. I write the Hydra in this way. So I take the head, rightmost head, I go 2 steps below, and then I look at the position over here. And then I have here a finite tree and a head. Nothing else. And then I go to H, which is the form. This tree is multiplied how many times? But it doesn't matter whether it's I or I plus 1, it's all fine. Now I introduce the fundamental sequences. And now the point is the fundamental sequence of omega to the gamma plus 1. X plus omega to the gamma times x plus 1. And then we basically see a bit, here's a sort of codification of this order. And here, this head is missing in the exponent, that's gamma, and is multiplied by this factor. So you see already what I'm hunting for, namely modeling the Hydra battle using the fundamental sequences. And of course, fundamental sequences were continuous. So basically it was something like omega to the lambda of x with omega to the lambda of x. So meaning if I have this situation somewhere in exponent, I have here some sort of continuity argument to move this structure also upwards. That's also fine. And then I have here some remaining context. For this I use also continuity in alpha plus lambda of x. It's alpha plus lambda of x in case that you have here kind of normal function. Okay, that's basically our idea. And now I have an intermezzo, namely, I just connect class E, the famous open problem in logic. Let Sk be the least set containing the function from n to n, such that the functions constant 0 and the identity function are in Sk, and such that these functions if g is Sk, the pointwise addition function, pointwise multiplication function, and f to the g are Sk, and define f below g by eventual domination. And what's known? Sk, this oscillation is a well order. That's the theorem. And the open problem is question is the Sk oscillation order isomorphic and E.
Sorry, it's perhaps a bit late, but is it possible, like, not to use the first leftmost 5 centimeters of the blackboard? It's a bit late, but because it's not feasible.
I move
The other board is perfectly visible, but it's just leftmost.
Is
this
it
is
better
also
now?
possible. Oh, thank you. That's also a good option.
Well, all sorts of options are possible. Just
it's important that you complain because I don't see. But this is an open question, and if you want to become famous, give it a try. The warning is it is open for basically 100 years, and I'm sure that it will be hard. So you can win a prize if you can solve it. Well, it's one of the most intriguing problems on elementary stuff, just involving plus, times, and exponentiation. Nothing is more simple than this one. In the lecture, we will learn also why this is a well-founded relation. By number theory, one can show that this is a linear ordering. So this is a superset of this one. So if this is a linear ordering, then this is, of course, all the linearly ordered. Now, what is the problem here? The problem is this strange exponentiation. So it's difficult to move into this Coulomb class, but in this Coulomb class, you have only the identity function as the base of the exponential function. And here you have an arbitrary f. This makes it messy, but you can give it a try. Maybe you can win a Fields medal with this. That I don't know. But just to explain some nice problem, well, this will not be part of the lecture, it's just for general information. So I also looked into this, but I didn't achieve much. So what is known is the order type function f smaller than this. In this Coulomb class is omega to omega. So same as the order type of alpha. Alpha smaller than this. That is known, but if you go beyond the double exponential function, you run into problems. So there's a recent publication by Berarducci where he's going by u to the 2, then x to the n. So, but even this is hard. Anyway, we are doing simple stuff. So basically, we show that fundamental sequences are behaving properly. So if you have a limit number, then the fundamental sequences converge as expected. or maybe I didn't define what convergence means, but will become clear from the next assertion. So beta is smaller than alpha, alpha is the limit, then there will be some element in the fundamental sequence of n dominating beta. So in that sense, the alpha n's converge to alpha. If I take an upper element beta smaller than alpha, then beta will at some moment be smaller than alpha n. Now the interesting thing is, can we calculate effectively this n as a function in beta? And the answer is yes. If we know that the maximum coefficient of beta is less than equal to n, then there's this indication. Now remember, what was the maximum coefficient? Maximum coefficient of omega to the alpha times m plus beta. It's the maximum taken over n, maximum coefficient of alpha, maximum coefficient of beta. And this explains in our context the role of the maximum coefficient, namely it gives a modulus of convergence. Somewhat interesting. And this is not obvious. This one is somewhat obvious. Now we had this stepping down relation. So what was this? Alpha stepping down. Beta means alpha is bigger than 0. And the expression m bigger than 0, such that if I take alpha and jump down, I is taking the same x and many times like somehow in beta. Now, if I can step down from alpha to beta, then assuming the gamma plus alpha is in normal form, I can step down gamma plus beta. So this I assume in normal form, and it also gamma plus comma alpha. That these sums behave nicely. Now, where is it needed that these normal forms are imposed? Because in defining the fundamental sequence, I have written alpha in normal form. Then I've applied the normal form to the rightmost exponent. If I have here an arbitrary sum, something strange can happen. So if I don't have this condition, it could be that the critical exponent is waiting in gamma, but then it's sort of, I have only information from alpha with respect to beta, and so it has to be conserved. So when I have context coming from the left, which don't disturb alpha and beta, then I can use the stepping down continuity to go away. And the fourth one is then easy, like I can go from alpha down to beta. Then I can consider what's going to happen with omega to the answer. Of course, you can expect something like this. Now comes a very important property. Namely, if I can squeeze in beta between alpha and alpha x, then beta cannot just leave this interval easily between alpha x and alpha. So if I step down along an arbitrary number n to be 0, I will not go beyond below alpha x. It's so-called Bachmann property. We don't see why it's useful right now, but this is a crucial property when you deal with functions indexed by ordinals, functions indexed by elements in E. Then once we have proper hierarchies, this property is crucial. And there's guaranteed the monotonicity properties of these hierarchies. And then some easy stuff, namely I have lambda equals 1, so lambda is a limit The successor is also true. There's lambda x plus 1 and lambda x. And the question is, step down along an arbitrary number, let's say y could be equal to 0. When I start from lambda x plus 1, I will always hit lambda x at some point. It's not possible to go below. So I had this strange example before. If I have here omega, that will be 1000. I step down along 100. And then at some moment, I just jump below this number. This I want to avoid. So I want to the left have only numbers. When I step down, that I finally hit this number. What is going to happen with fundamental sequences? You cannot just jump directly below this number. But someone first you have to hit this number, and then you can continue. Consequence of this one. The slight refinement of this one is the following. This number is bigger than 0. Then I have even the following, namely that I have here, can you smuggle in a +1? And here, if lambda is a successor, then I have here equality. And otherwise, lambda is a limit, and here is a strict inequality. Okay. But this +1 is, let's say, this is true. Good question. I would say lambda is a limit. So if lambda is 0, this is wrong. And if lambda is a successor, it's also wrong. So we have to assume that lambda is a limit. This one holds also for moments. Okay. Now we have to prove this. What is the trick with all these things? The trick is, of course, not the proofs are not difficult. The trick is basically you have some result in mind, and then you have to develop some theory. So, and then you have to set up the theory in a way that one piece fits together with the next piece, and when all pieces fit together, then you have a theory, and when they don't fit together, then you have to come up with a new formulation of lemmas. But we just take this as it is, and it will be easy to verify it. But small steps will finally produce large complexities. Anyway, so the first follows from the second. Because 2 basically gives an effective modulus of convergence for alpha. Now, so let us prove 2. For this, write alpha in normal form. First comes the most complex exponent, then finally many of those, plus omega to the alpha L times L. So what does normal form mean? It means that the mi are different from 0, and alpha I is bigger than alpha. Note I have written the normal form condition slightly different in my definition. I have a weakly descending chain of ordinates of exponents, but here with these numbers I collect the equal terms, and that's the same stuff. Beta is written the same way. Then we have here n pi 0 and inter I bigger than beta. Okay, what can happen? It could be, so we have alpha is bigger than beta. So it could be that beta is just an initial segment of alpha. So if we have the situation L is bigger than R, and alpha is of the beta line, and m line for R less than R. And what's going to happen? Okay, alpha is a limit. This means this last one is non-zero. Well, then omega to the alpha L is NL. Now this evaluated with N. And if you have here a limit ordinal and we evaluated at N, it will never be zero. It will be bigger than zero. And the reason for this is we have written omega to the gamma plus 1 of x is omega to the gamma times x by 1. Now you see it's plus 1. Plus 1 is important to guarantee that fundamental sequences don't hit zero. Otherwise, if it's a zero, it could be zero over here. That is not the case. So this is not hitting zero. So if I go down at this number, if this term is just overshooting, not showing up here, so alpha at n is context plus last term at n. This is not zero, and if this term is not zero, then the whole thing is bigger than this number. Alpha of n is bigger than 1. Okay. Now, what else can happen? We have alpha is bigger than beta. Now, it could happen that there is a position I where we make the difference. So if there is I smaller than n, such that beta I is smaller than alpha, or we have that beta I is equal to alpha I, and ni is smaller than ni. Which means the I term here is bigger than the I term here. And this case distinction makes that alpha is bigger than E. Now, if this happens for some I smaller than L, this term here still existing. We have and this is still than 0. And so if we take alpha at argument n, the term at position I, which makes alpha bigger than beta, still existing in alpha n. And since this I term is still existing in alpha n, we have that alpha n is bigger than beta. Because the I term, omega to the alpha I times mi, is also showing up in alpha n. Okay. So what? So finally assume so we have a lexicographic comparison of alpha with beta. If the comparison is at the position I smaller than L, we are done. So now we have to look at the last position L. Finally assume that, and then we take the terms in beta. And look at the corresponding term in alpha. And this has to be the case. Okay, now we have to make, so if this is bigger than this was the argument by alpha is bigger than beta. Now we have to figure out what's going to happen with the fundamental sequence. Okay, so it could be that alpha L is the successor. So this one is bigger than this one. What did I write over here? Yeah. Yeah, okay. We make this case, and now we assume that alpha L is bigger than beta L. Gamma is the other case will be that alpha L is equal to beta L, but that's different. Let's first assume that alpha L is bigger than beta L. It could be that alpha L is a successor. Then what? Take one of those. And consider the fundamental sequence. This is omega gamma times n plus 1. Gamma is at least as big as beta L. So this is bigger than beta L. Okay. What do we know? We know the maximal coefficient of beta is less than equal to n. This means the maximal coefficient of beta collects, for example, this NL. NL is less than equal to n. N is strictly smaller than n plus 1. So this will be bigger than omega to the beta L times NL. So that's omega to the beta R times n. Because omega to the beta times omega to the beta L times n is indeed as big as this one. And then there's the last one, omega to the beta L. The beta L is bigger than all the remaining exponents. So we have this one bigger than this one. So the fundamental sequence, try to this number n, the last term of the sum, is already bigger than the whole rest. This holds because n is a maximum. Then we have alpha n is bigger than n. Next case is alpha L the limit. And alpha L is bigger than now the maximal coefficient of beta is designated to n. Beta L is a subterm of beta. So the maximal coefficient of beta L is also to be. The maximal coefficient of beta L is bounded by the maximal coefficient of beta, therefore bounded by n. Now we have beta L smaller than alpha L. Alpha L is the limit. Induction hypothesis shows beta L will be bounded by so we prove this one by induction on alpha. Here we have applied the induction hypothesis. And actually we have a strict model, right? First it's strict one. This means what? Omega to the alpha L of n is bigger than omega to the beta L times NL omega to the beta R times N. Because alpha L at n is bigger than the first one, but all the other exponents are smaller than beta L, therefore this is going to hold. And then it follows that alpha n is bigger than beta. For the last term in alpha after taking fundamental sequence is already bigger than this remainder. So what else can happen? We have this is smaller than this one. We discussed the case beta L is smaller than alpha L. Now it could be that beta L is equal to alpha L, and we have to use that NL is smaller than ML. So if beta L is equal to alpha L and NL is smaller than ML, then what? Well, omega is beta L plus 1 times NL plus 1 plus omega to the beta R times NR is bounded by omega to the alpha L of N. Since by induction hypothesis, so we know alpha L is equal to beta L, but beta L is strictly bigger than beta L plus 1. The induction hypothesis gives what? Question? Well, I want to conclude that beta L plus 1 is bounded by alpha L of N. That is true, but this only works if alpha L is a limit. Well, let's consider this one. But if this is done, then beta is 4. Omega to the alpha 1 plus omega to the beta L times NL. So the alpha I and the beta I are the same up to L. NL was smaller than ML. Here we have plus omega to the beta L plus 1 times NL plus 1 plus omega beta R times NL. This one here is bounded by omega to the alpha L n. Okay, so this is bounded by omega to the alpha 1 n1 plus omega to the alpha L ml minus 1, because ml is bigger than ml minus 1 is at least as big as nl, so this one is at least as big one, this one. And omega to the alpha L of n, this one is bigger than this one. And this is alpha n. So you see, it's messy, but anyway, there's one case which I forgot in my notes, namely when alpha L is a successor. So we have to figure out what's going to happen then. But don't worry, the results should work easily. So assume now finally that alpha L is sensor. Okay. What is alpha n? Alpha n is omega to the alpha 1 plus omega to the alpha L times ml minus 1 plus omega to the alpha L at argument n. Alpha L is a successor, so we have here gamma and here times gamma s. What is beta? Let's form starts with the same numbers. Become omega beta L times N plus some rest. If omega beta L plus 1 times ML plus 1 omega beta R times N. Right? Now the magic comes. ML plus 1 is element of the maximum coefficient of beta. So this number here is less than equal to n, but here's an n plus 1. Find n plus 1 gives an omega to the gamma, where gamma is bigger than all the exponents over here. So this time, this thing here is smaller than this. Therefore, we are also fine in the case that alpha L is a successor. Now, this proof is not completely simple because you have to go through all the case distinctions, but you see it works out. Yeah. Now, was a difficult part. Now comes something easy, namely proof of 3. So what do we know? We have alpha steps down to beta. What does this mean? We have alpha goes down and one step at alpha of x. And it goes down to alpha of x. At some moment, we have beta. Now we have to know about if we have normal form gamma and alpha. We have normal form gamma and alpha x. Remember, what does normal form mean? Normal form means you write gamma this way, and then you write alpha this way. That alpha 1 is less than or equal to gamma n. Now, when you form fundamental sequences here, what you do is you cut off stuff from the right, but you will either not affect the alpha 1. The alpha 1 still becomes the same, so it's smaller than this equal to this one. Or at some moment you have eaten all stuff away, and then you make alpha 1 small. So you see that this one is going to happen. And by iteration, this means normal form holds for gamma alpha x. All these terms. That's good. And now if we have normal form of gamma and alpha, this implies that gamma plus alpha is same as gamma plus alpha x. When you have this nice descending sequence, you put in a gamma always at the left. And you see, you can use the original sequence and just plug in gammas to the left, and then you get the new sequence as required. So this is an easy proof. It takes a sequence witnessing this one, and adding a gamma in the sequence, you will get a sequence witnessing this one. Now we take 4. Proof of 4. It's also somehow by induction on ordinals. So what do we have to show? So by induction. So it suffices. So that from omega of alpha can step down along x omega of alpha. Now, once you have achieved this, you can apply induction hypothesis to this one, and then the result continues. Right? So if you can show this one, let me write it out. So alpha steps down to alpha of x, steps down to alpha x, x And if you have this one, then omega to the alpha steps down and finally many steps to omega to the alpha x. Omega to the alpha x go and finally many steps to omega to the alpha x of x using this one. Finally goes to omega to the beta. Now there's a difference with this proof. Namely, it looks very similar, but we haven't proved this one yet. So if you have this one, it's fine. This one works. So if alpha is the limit, then of course omega to the alpha x goes on one step down, omega to the alpha x. Therefore, this is true. But it could be that alpha is a successor. And what's going to happen? Then omega to the alpha of x, omega to the gamma times x plus 1. So this is omega to the gamma plus omega to the gamma times x. Now we step down along x. And basically, omega to the gamma times x, if you step down along x, at some moment you hit 0. This requires many steps, usually more than one step. But this is the same as omega. So the proof is easy, but what is the point? The point here is you here use m many steps, so from alpha to beta. You might need an astronomical number of steps to go from omega to the alpha to omega to the beta. So the number of steps can here be much, much bigger than the number of steps needed here. Because you have to count how many steps are needed to kill this non-zero term. But at some moment, you jump down with the ordinate, at some moment you hit 0, and but you don't know how much time it needs. And this can be take very long. Okay, so you have proved this one. This one was easy, this one was easy, this one was difficult. More difficult, and this one is also medium difficult, but important. So I will prove this. The difficult means it's mathematically not really difficult, but it requires just some sort of case distinctions. So proof of 5. We assume what? Alpha x smaller than beta, smaller than alpha. Now, if beta is a successor, then beta n is a predecessor. The predecessor will always be bigger than this one. Then it's simple. We may assume that beta is something like that. Now, next thing is we write down what is alpha. Alpha can be a sum. So alpha, normal form, also form omega to the alpha 1 plus omega to the alpha n. And then what's going to happen? Then we have alpha x. It's omega to the alpha 1 plus omega to the alpha mx smaller than beta smaller than omega to the alpha 1 plus omega to the alpha n. What does this mean? This means beta has a specific form. Okay, so think we can show that beta necessarily is a form omega to the alpha 1 plus alpha m minus 1 plus some gamma, where omega alpha m is than gamma, than omega to the alpha m. Okay. Now we prove 5 by induction. Let's say induction on alpha. So here we have a situation. So assuming that m is bigger than 1, we can apply induction hypothesis. Saying that omega to the alpha m is equal to gamma n more than omega to the alpha m. And if beta is this form, then beta n by continuity is a form. Is this form. But when you compare beta n with this term, then you see that beta n is bigger than alpha x because gamma n sits above this term.
And with the n in gamma n, it's not the same n as omega to the alpha n. It's just
did I write omega to the alpha n? It's m.
okay.
Yeah, it should not be the same. That's for sure. Otherwise, problems. Okay, then we have that alpha is equal to beta n. What does this mean? This means we can simplify our situation, namely, now assume basically that m is equal to 1. So we squeeze in beta. Be careful. Beta in between alpha n and alpha, having this situation. Well, certain cases can show up. Assume that alpha 1 is successful. Then we would have omega to the gamma times n plus 1 smaller than beta smaller than omega to the gamma plus 1. Now the only way that beta can be squeezed into those two terms, then beta omega to the gamma times n plus 1 plus delta is delta bigger than 0. Now beta n is number plus delta n. Delta n is at least as big as 0. And therefore beta n at least as big as omega to the gamma n plus 1, which is omega to the alpha 1. So we reduce the case where alpha 1 is the limit. So finally, So alpha 1 is the limit at this time. Now we look at beta. So we have alpha 1 is a limit, so omega to the alpha 1 of x, which is omega to the alpha 1 of x, followed by beta more than omega to the alpha 1. Now beta could be, if beta has a sum, let's say omega to the beta 1 plus some delta bigger than 0. Then we are fine, because if you squeeze in beta between those two numbers, then this will be the case that alpha 1 of this is equal to beta 1. Because otherwise, if beta 1 is strictly smaller than this one, then the whole term would be strictly smaller than this one, because this one is closed under addition. Okay. What's going to happen? And beta n is omega to the beta 1 plus delta of n. This is because omega to the beta 1. And this is because omega to the other 1 of x. So you can assume that beta is also an exponential. So assume beta is omega to the beta 1. Sitting in this interval, then we have what? Alpha 1 of x smaller than beta 1, smaller than alpha 1. Aha. Now, can apply induction hypothesis for alpha 1. What follows is that alpha 1 of x is equal to beta 1 of n. Now, we are not yet done, almost. If beta 1 would be a limit, then you would obtain that omega to the alpha 1 of x, which we know is less than equal to omega to the beta 1 of n. This would be equal to beta of n. Now, that's fine. What is remaining? Remaining is in the case that beta 1 is a successor. So what do we have? We have alpha 1 of x smaller than beta 1, smaller than alpha. Now, if this is a successor, then alpha 1 of x is less than equal to gamma. Okay, and then omega to the alpha 1 of x less than equal to omega to the gamma, less than equal to omega to the gamma times n plus 1, which is omega to the gamma at element n. So omega to the gamma plus 1, which is omega to the beta. Now, there's one point which you have to be aware of. What is a point? It's a point that every now and then I use that here as the plus 1. Namely, if there would be just times n, n could be 0, and then the argument would be killed. So if I would have defined omega gamma plus 1 n is omega to the gamma times n, then this property would not hold because I have these strange cancellations. Now that's not dangerous. You have to be, so when you're dealing with fundamental sequences, you have first to check, oh, is this defined? And if it's defined in this way, then at this moment you have this assumption only when n is at least as big as 1. Then the same argument works. So here's n equal to 0 allowed because I was using the n plus 1. But when you have times n, then you should just work with positive numbers. Then the rest is fine. Okay. Now, that was, as I said, difficult. It's not really difficult. Just make case distinction, then it comes out naturally. Now let us prove this one. Is this easy? The answer is yes. It's not easy using property 5. So I reserve a bit of space, but you see the small amount. How can we produce this? Well, we have here lambda x, and we have here lambda. And of course, if lambda is the successor, it's trivially true, because in both cases we jump to the predecessor. So assume that lambda is a limit. Then you have lambda x plus 1 for here. Aha. Now you can apply number 5. So here's an arbitrary y. Y could be this n. Then by 5, you have lambda x. It's equal to lambda x for 1 at 1. More than 1. Now, two cases. Either I fit the number, then I'm fine, or this is bigger. When it's bigger, I do the next one. Either I hit this number or I'm staying above. So just by iteration of 5, let's see finally 6 follows. So it was easy. Now we have this one here. And it does not follow directly from 5. So you have to be careful. It's also somehow simple. Just using we prove 7 by induction on lambda. So assume lambda is equal omega to the alpha 1 plus omega to the alpha m. Here the alpha m is a dot. Now, of course, in cases, alpha m can be gamma plus 1. So what is then lambda of the x plus 1? Omega to the alpha 1 plus omega to the gamma times x plus 1 plus 1 times x plus 2. Now you write it in the following way as x plus 1 plus omega to the gamma. And now he takes this number, omega to the gamma, and step down along y. Then the claim is some moment I need one. Why is this the case? Well, by induction on gamma. So if gamma is a limit, I step down to omega to the gamma of y. Induction hypothesis, I'm done. If gamma is the successor, then omega to the gamma steps down at y. So it goes to, if gamma is the successor, it goes to y, omega to the gamma times y plus 2. And then one of the omega gammas is at least as big as 1, and so I'm done. Finally, it could be what? That gamma is equal to 0, but omega to the 0 is as good as 1, so it's also fine. So this goes to capital Y to omega to the alpha 1 plus omega to the gamma times x plus 1 plus 1 plus lambda. What else can happen? Alpha m could be a limit. So, what is that? Lambda equals 1. Omega to the alpha 1 plus omega to the alpha m of x plus 1. Oh, alpha m plus alpha m x plus 1 steps down along y to alpha m of x plus 1. Now, by using properties 3 and 4, steps down to omega to the alpha 1 plus omega to the alpha m x plus 1. Now this steps down to omega to the alpha 1 plus omega to the alpha m x times y plus stepping down something like this. And well, this is stepping down to omega alpha 1 plus omega alpha m x. And here y plus 2, but I just need 1 plus 1. So what is here the point? Y could be 0. I need one term for this one, then one last term for the 1. So you might ask where I did use that y is bigger than 0. But just here to guarantee that I have here at least 2 terms, one for this one and one for the 1. Okay. Now we are already time out, so to say. So I will stop here. What is going to happen next time? Next time we define the right hierarchy. 0 of x is x. H alpha plus 1 of x is H alpha of x plus 1. H lambda of x is basically H lambda of x plus 1. And these functions are used. H omega to the omega corresponds to the Ackermann function. But now you can imagine if you have omega to the omega to the omega, then you get more than the Ackermann. So what you will get is the general function of all Ackermann functions in n variables. Now you have a tower of height 3, but now you take the next tower of height 4, and then you exceed whatever you can imagine. And Hydra battle actually is
Sorry,
Yeah.
could you just shift the camera a little bit?
H omega x of x. Omega x is a power of omegas, so extremely powerful. And that's basically a sharp match. So the time needed to kill the Hydra is measured in terms of these Hardy functions. And the Hardy function has a property that this function cannot be proved in total in arithmetic. And when you have your fixed D, the totality can be proved. So if you fight against Hydras of a bounded height, you will win in P-arithmetic. And when you fight against Hydras of unbounded height, you are not able to win within P-arithmetic. Okay, but this is for the next time.
Okay, so see you next time.